we'll have another example in this video. We consider an LTI filter. We call it a moving average filter. The relationship between input and output is described by this relationship. Basically, what it is that this is time. At time, any time t, we take an interval of time t minus cap t, and then time t plus cap t. So this interval is length of 2t, and then we integrate the random process over this interval, whatever it is, with the area of this random process, and then divide it by the length. So this is the average of x of t over an interval of t minus cap t and t plus cap t. So this is just average because we divide it by the length. So this is called the moving average. So this filter is linear because if you double this one, if you multiply this, and if you add two components, you will have the same two components. So it's linear, and it is time invariant because if you delay input, you will get the same delay at the output. So therefore, I should be able to describe these as a convolution. Convolution integral is h of, let's say, t minus alpha, and then x of alpha d alpha from varies from minus infinity to plus infinity, because the boundary of these two integrals are different. So the h of t here shall be 0 outside of this interval. So h of t minus alpha shall be, because this is h of t minus alpha, shall be equal to 1 over 2t if this alpha is equal to t minus t, if alpha is between t minus cap t and between t plus cap t, okay, and 0 otherwise. Okay, so in both sides of this equation, I could replace t minus alpha by x or whatever. So I replace this by let's say another dummy variable, let's say gamma. So h of gamma will become equal to 1 over 2t if gamma is between t and minus t and 0 otherwise. So this is, if I plotted the impulse response h of t, and this is t between minus t and t, so this will become a rectangular pulse of 1 over 2t. Okay, so this is called a moving average filter. So basically here y of t is equal to x of t convolved with this h of t, which we call it a rectangular pulse. If x of t is convolved with this one, you get this one. So what you can do, you can calculate h of t convolved with h conjugate of t. So Fourier transform of that is equal to h of omega, and this one will be h conjugate of omega, and is equal to h of omega to the power of 2. This is power gain of the filter. Okay, so if the input is White-Sense stationary, the input and output shall be also jointly White-Sense stationary because we have an LTI filter. So in that case, I would have SYY of omega will become equal to SXX of omega times h of omega to the power of 2. For this one, if you calculate h of omega, you get a sinc function. The Fourier transform of this pulse is equal to integral, this is equal to 1 over 2t, and this function is 0 outside of the interval minus t to t. So I have the integral t from minus cap t to cap t of e to the power j omega t dt. And then you can, using your calculus, you can calculate integral, and it's going to be equal to. So this is a sinc function. So if you plot it in a frequency domain, you get some function like that. So at frequency 0, you get the highest peak, and these 0 crossings are periodic, except at omega equals 0, because you will get 0 divided by 0, and the limit is going to be equal to 1. So when you calculate this one, whatever is the power spectrum of the input, so if let's say xx of omega, if you have some power spectral density, you have to multiply these by this sinc to the power of 2. So you get power this one multiplied by this one. So this is what we get. So you filter. So it's kind of be the power spectral density, whatever you have, is multiplied by this sinc to the power of 2, and then these high frequency components are attenuated. DC components are not touched because this is almost equal 1 around frequencies close to 0, and close to these 0 crossings, the energy of the output is going to be 0.